Thank you for joining us today. I am Kent Shesky, and I serve as the Executive Vice President of the Council for Agricultural Science and Technology, or CAST. Very pleased to share our most recent CAST issue paper on ground and aerial robots for agricultural production, opportunities and challenges. As noted on the agenda, we'll have a Q&A session with a panel of the authors from this issue paper's task force after our main presentation, and we'll be opening up the chat box for questions related to this topic a few minutes in advance. CAST was formed in 1972 to provide unbiased, credible, science-based information about food and agriculture to policymakers, the media, the private sector, and the public. CAST is a membership-based organization comprised of scientific and professional societies, nonprofit organizations, universities, companies, and many individuals. It is through our network of members and supporters that we select our topics for CAST papers and access volunteer scientists, economists, engineers, and other subject matter specialists who help produce our papers. Over the past 13 years, over 1,500 professionals have graciously volunteered their time, energy, and expertise to serve as authors of our papers or as reviewers who ensure each is unbiased and based upon sound science. CAST produces several different types of publications. Accompanying each publication is a one-page summary called an Ag Quickcast, and also a student study guide for use by educators and students. The use of social media is an important part of our science communication efforts, and I invite you to join us on any of these platforms. Today's webinar is being recorded and will be available later through our website. Toward the end of our main presentation, we'll post a message in the chat box that is open for you to submit questions to our panelists. The task force chair for this paper is Dr. Santosh Pitla with the University of Nebraska-Lincoln. Dr. Pitla is an associate professor in the Department of Biological Systems Engineering. His postdoc work dealt with modeling the economics of autonomous agricultural machines relative to conventional machines for corn and soybean production. His duties at UNL include teaching technology students and developing a research program focused on advanced machinery systems for row crop production. I will now turn the program over to Dr. Pitla to lead the presentation. Thank you, Dr. Pitla. Dr. Pitla, I think you're muted.
Can you all hear me okay?
Yes.
Sorry, I couldn't find the unmute button. And also, can you see me okay? Melissa, maybe you have the control over the video too. Thank you. Yeah, I couldn't find those buttons to unmute. Thank you all very much. Ken, thank you very much for that kind of introduction and giving me the opportunity to present this work that many of us put together. So first of all, I would like to recognize all the task force members without whose help this paper would not have been possible, and also the reviewers who really helped improve this paper with their valuable feedback. And I would also like to thank the CAST liaisons. So overview of this ground and aerial robotics paper. I'll go over the introduction and background, where I'll talk about historical trends of mechanized agriculture, and I'll talk about a broad classification of agricultural robots. And I'll talk about robots in context of row crops, orchard and specialty crops, and then robots in animal agriculture. And we'll identify some key enabling factors for the deployment and adoption of robots, followed by conclusions and task force recommendations. So if you look at 1900s, we literally used horsepower for farming operations. And in 1920s is when tractors were introduced. And fast forward 100 years, today we are looking at high horsepower machines. As an example here, you could see a 600 horsepower tractor, a very high-tech machine. And today machines that are offered come with the option of connecting to the cloud. And also these can do auto steer very precisely with the RTK GPS accuracy. And we're also now using drones or unmanned aerial systems that can easily fly over fields to observe crop conditions, but also look at crop corn plant stands, and then we're also using for weed identification. So those are some of the examples. So how are the machines going to look like in the future? So we are looking at machineries, something like these on the top right. So there could be robotic machines. Some of them could be smaller machines that can grow underneath the crop canopy, and some of them could be high clearance robots. And then there could be drones that are actually spraying in the fields. And here you can see an example of a weeding ground robot in a vineyard. And these are just very few examples of many robotic platforms that are under development, both at research institutes, but also in OEMs and also startup companies. So there's a comprehensive list of these robotic platforms at the link here. When we look at orchard crops or specialty crops, we have apple harvesting robots and then robotic milking stations. So as you can see, there are a variety of robots that are used for both crop production and animal agriculture. So here's a classification, very broad classification of agricultural robots. So these are divided into unmanned ground vehicles, unmanned aerial systems, and robotic manipulators. UGVs or unmanned ground vehicles are used in both row crops and specialty crops. So you have UAS used primarily for sensing, but now we're looking at spot spraying or targeted chemical spraying. And robotic manipulators are predominantly used in greenhouse and phenotyping applications, your livestock, and then specialty crops. Robotic manipulators are nothing but robotic arms. And robotic milking stations is a mature technology that have been used for many years. So you could see a combination of these robots. For example, a robotic manipulator could be mounted in an unmanned ground vehicle for automating field operations. So the vision is, I think we are approaching a connected farm where you have unmanned aerial systems that are flying over the fields, looking at problems at a high level. And then you have some ground robots that can go underneath the canopy, like robot 1 and 2 here. And then you have some high clearance robots like 4 and 3, 3 and 4 here, which are going through the crop, not only sensing the crop, but also doing some sort of application. And then some of the computing is happening on the machine itself or edge computing devices, and some of the computationally intensive operation could be happening on the cloud. And we have these robotic manipulators that could be inside the barn, milking the cows, but also providing feed delivery or phenotyping the animals. So as you can see, there is a variety of robots that could be a part of the connected farm of the future. So where we are today with this vision, so companies are offering autonomous grain cart solutions. As you can see here, this is a good example, a tractor pulling a grain cart. This is a typical 200 to 300 horsepower tractor. As you can see, there's no operator. So here the idea is the combine operator can summon this autonomous grain cart so that you can autonomously transfer the grain and unload it at the edge of the field. So there are machines that are being offered that don't look like typical tractors. So this is a DOT platform by Raven. So this is a modular machine. You could use multiple operations with this type of machine. So these two machines are between the ranges of 200 to 300 horsepower. So we're talking about high horsepower machines getting fully autonomous. So there is work in the research side too at the research institutes, and one of the examples is this robot that we are working at University of Nebraska-Lincoln. So there is many work. There are many robotic platforms that researchers are working on, which are electric machines. So this robot is a 60 horsepower internal combustion engine. So very more practical field platform that we are trying to develop. And this is used for collecting soybean plot information. Here is we're using it as a phenotyping application. But since it has 60 horsepower, we could do other operations too with this machine here. And then we also are using robotic manipulators to phenotype corn and sorghum plants inside the greenhouse. The idea here is this: you can place this robotic arm next to a conveyor belt, and then we can do in vivo sensing. So here, this robotic gripper is sensing the chlorophyll content and the leaf temperature. So as you can see, there is work both from the startup companies and the OEMs, and also at the research institutes on robotics for row crops. So we are moving towards small autonomous machines. Here's a good example. This is by Savanto Ag. There's a small robotic tractor. And then this is, we are using a swarm of machines, multiple ground robots. And the idea here is replacing one big machine with multiple smaller machines. And the motivation for that is the ability to reduce the risk. So for example, if you have 10 machines working in the field, even if one of the machine is down, the remaining 9 machines can still work, right? So that's how you're managing risk. And also there are benefits in terms of reducing the soil compaction. So that's kind of been the motivation to go small but use multiple machines. And something that is coming up is farming as a service. So instead of the producer buying these machines, these companies are offering this as a service, like a custom operation. So in terms of aerial robots in row crops, predominantly we have seen work in the area of sensing crop and identifying crop stress. So here's an example. You can see this is a multi-rotor UAS collecting information from soybean plots. So US has been used for corn population counts and then weed identification. So a lot of machine learning and AI techniques are used to differentiate between crop and weeds. And now with the increase, the UAS are advancing at a really fast pace. Now companies are starting to offer drones that can actually spray. So they can handle higher payloads now. So when it comes to robotics in specialty crops, like orchards here in this case, one of the biggest challenges is availability of seasonal labor for harvesting. So there's a lot of work in automating the harvest process or the fruit picking process. So in this case, this is an example where you have a robotic manipulator mounted on a ground vehicle. The ground vehicle could be a ground robot too. So it will get close to the tree and the robotic arm is going to pick the apples. So one of the important thing is when you're picking, you shouldn't damage these apples. So you have soft grippers. And another challenge in this picking process is the occlusion. Occlusion is nothing but one fruit being in front of the another. So the machine has to use like really good algorithms and machine vision techniques to differentiate between the two fruits and pick the fruit. So because of that, some of the computationally intensive process, these robots are still slower than human labor. So humans still pick faster than the robots can. So that's been a challenge. And UAS are used for some specialized applications, such as this one here. where this UAV is trying to deter bird pests in a vineyard. So again, with the advances, there are a lot more applications that are coming up in using UAS for crop production. So I'll go over some challenges here. So ground and aerial robots in row crops. So the technical challenges has been, designing effective control architectures and AI algorithms, not only for operating one individual UAV, but also a fleet of UGVs. So how do we distribute tasks among multiple UGVs? Are they doing the same tasks or different tasks? And there could be humans in the loop and without humans working with the robots. So there's a lot of work, and this has been a hot research area, and there's a lot of work that is happening. And then designing and deploying robots to work faster and more gently than human labor when interacting with both plants and animals. Some of these socio-economic challenges include the fear associated with robots in terms of replacing human labor, and also what is the economic feasibility of both large and small acreage farms, like a large producer versus a small acreage producers. What is the economic feasibility of robots? And then liability, security, and data privacy concerns associated with the ground robots. So these are still up and coming. So there's still a lot of work need to be done in this area. So in terms of aerial robot, small UAS cannot operate in high winds or medium precipitation. And then there are battery and payload limitations. And then we still cannot operate a UAS fully autonomous, right? So there still need to be a person monitoring it. So federal regulations prohibit that operation. And limited number of US manufacturers may present future challenges. So there's only 3/4 of all multi-rotor UAS is manufactured by one company. So there needs to be more manufacturers doing this. And then very little data are available to show economic benefits of UAS to row crop producers. So more economic studies are required in this area. So in terms of robotics in animal industry, so there are 35,000 automated milking stations. So the robotic milking stations are very mature technology and has been used over many years. So one of the things in this area is there's a debate on what is animal welfare of cows in indoor environments. So hopefully automated milking stations will take into account some of these societal concerns as we move forward with the robotic milking station deployment. And coming to poultry and swine industry, so robots are being developed to pick eggs laid on the floor, and also to turn the litter and sanitize the environment for poultry industry. In the pig production, the robots are up and coming, and here is an example of a robot. It's called BoarBot, and this robot will put the pig on a leash, and it can take the pig around in the pen, especially during the breeding season. So there are enabling factors for the deployment and adoption of robots in agriculture. So here are some of the very important factors, enabling factors, machine vision and AI. So in addition to traditional closed loop control systems on robotics, the machine vision and AI is at the core of robotics. So in the last 2 years, there have been many advancements in this area, and more are needed. And big data and cyber infrastructure. This is a really important factor, not just for robotics, but for the whole ag ecosystem. But think about robots that don't have operators on them. So there'll be more data generated by the machines. So that's why big data and cyber infrastructure is going to be a key. And farm connectivity is going to be an important one, primarily for logistics. So if a robot is out of seed or fertilizer or chemicals, so it needs to communicate that with other robots or to a remote entity, so that the material logistics can happen. So, and then interdisciplinary workforce. So now we're at a stage we're working on different robotic machines, both at research institutes. The startup companies are working on this. Maybe 10 years we have robots and we will have workforce needs. So our traditional agriculture curriculum need to consider this and prepare our workforce for these future needs. And liability, security, and data privacy associated with robots. So there's been work in the data privacy area, but what happens, there's damage caused by a robot to another machine or property or an individual. So how does that mechanism look like? So we still don't have enough information on that. So conclusions. So while labor challenges are driving the demand for automation robotics in specialty crop production, optimal management of production inputs is driving the demand for robotics in row crop production. Use of UGVs in row crop production with the model farming as a service has the potential to serve both large acreage and small acreage farmers. And US are very effective technology tools. However, high initial capital cost and short flight time and payload capacity are limiting their widespread use. But now we are seeing heavy payloads being used on the US. So the technology is advancing at a fast pace. Robotic milking stations are mature and commercially available, whereas in poultry and swine industry, these systems are still evolving. And further research in assessing economic benefits is needed, both for ground and aerial robots in crop production. So multi-purpose robotic machines could present better economic viability. Just think about this as analogous to a tractor. A tractor is used for multiple operations. So we could use multi-purpose robotic machines, and they could be more economically viable. And connectivity will be very important for supporting AI-based technologies. Thinking about edge computing and computing on the cloud, connectivity is going to be very important. And interoperability of data sets for seamless sharing of data is important. So we have the robotics companies or robots working in the field, and we need to share the data with, let's say, with seed and chemical companies. So there has to be seamless sharing of data to enable effective decision making. And then talking about that workforce, experiential learning opportunities is one way to provide skills to the students in the area of ground and aerial robotics and IoT and AI, which is currently missing in traditional agriculture curriculums. And also ground and aerial robots can attract a new generation into the farming. The deployment of ground robots and aerial robots could result in liability and security concerns. In industries addressing the data privacy concerns. So we need to still get a better handle on the liability and security issues of the robots. So finally, the task force recommendations. Farmers have always been cautious about adopting new technologies. If the return on investment is proven, then there will be an increased adoption of appropriate technologies. So, and IoT providing field connectivity is a huge task. So there needs to be public-private partnership in developing innovative wireless solutions. I know there has been programs for NSF and USDA already in this area. And then safety and operational standards for robots are needed, because standards are necessary to address product liability for the OEMs. And also these will shorten the product design cycles, while integrating that, while ensuring that you're integrating these robotic systems safely in the production environment. And this first bullet point, this is valid for the entire ag ecosystem, and it is also true for agricultural robotics. So educational institutions, government agencies, and private sector must initiate a dialogue with policymakers regarding the data privacy, security, and ownership. So this is true for not just robotics, but also the entire ag ecosystem. And grounded aerial robots have a lot of benefits to offer, and the regulatory environment must keep pace with this changing landscape of agriculture. So those are the recommendations and conclusions. And again, I went through it, just the highlights of all these, and the details are in this paper. And I'll turn it over to Kent here, and then we'll do a Q&A sessions where we can answer more questions that you have. Thank you.
Thank you, Santosh, for that great overview of the paper. And again, if you have not accessed the paper, it's available on our website. Pausing briefly for our certified crop advisor attendees, here is the QR code for receiving your CEUs, and we're very pleased to work with your societies in helping make this possible. As we mentioned earlier, we're now going to be moving into a Q&A panel, and we are very pleased that we have a number of panelists joining us for the presentation today. They include Tami Brown-Brandl, professor at the University of Nebraska-Lincoln, Dennis Buckmaster, professor at Purdue University, Todd Janzen, president of Janzen Agricultural Law, Michael Sama, associate professor, University of Kentucky, and Scott Shearer, professor and chair at Ohio State University. Thank you all for joining us. Thanks for being a part of this program and also your work on the paper. Dr. Pitla, I'll turn it back over to you to start maybe sharing some of the questions that have been posed during the presentation that we will now open up for the panelists to comment on and share their thoughts.
Okay. Thank you, Ken. Yes, so pleased to see many questions. So I'll start from the top. So are there any robotic platforms for soil testing? In particular, Indigo Ag is interested in SOC and bulk density estimations.
I'm familiar with one. It's rogoag.com on your internet. RogoAg is a robotic soil sampling firm. It's sort of a skid steer based, but entirely autonomous. Once that vehicle leaves the trailer, you just watch it do its work. That's one that I know of.
Yeah, thank you, Dennis. Thanks for answering that. Yeah. And the second question is, you had mentioned that robotic fruit harvesting had not yet advanced to where it can replace human labor. How far are we from achieving that? And what are the gaps in technology to achieve this? I can answer that question. My research is not in apple harvesting, but based on the information provided by one of the co-authors, Manoj Karki. So I can answer that question. So I think currently robots, humans can harvest 3 to 5 times faster than a robotic arm. And especially in apple orchards. And I think there has been some work on actually changing the tree architecture, how the fruits are, to help the robotic systems. And also there are companies that are using multiple robotic arms to increase the speed of harvesting too. So hopefully that answered some questions there. And the third question is, I'm Ravichandran from Tamil Nadu. We do not use a lot of machines, though we can't afford one, we get it on custom hiring. Are these robots ground aerial suitable for smallholder farmers? Most of farmers are small and medium farmers. Are they compatible for such farmers? So I think this is a really important question. And this is where that farming as a service could be a solution, both for large and small acreages. And I would like Dr. Scott Shearer to share some of his thoughts on this. Dr. Shearer, can you hear us?
Sorry about that, Santosh.
No
I forgot to unmute myself.
Okay.
As we look at and think towards the future about how some of this technology is going to make it into actual practice, I think when we look at North America and then we begin thinking about how this is going to manifest itself around the world, I think farming as a service becomes one of those issues where the technology can be, I guess, rolled out to a lot of different people in a lot of different locations in a very cost-effective manner. It makes the technology much more scale neutral in some respects. Mm-hmm. Obviously, there's going to need to be a critical mass of landowners or farmers in a particular region that want to take advantage of the technology to support that those evolving businesses. But I think in a lot of rural areas, could be in developing countries, could be in developed countries, there's going to be some opportunities, some tremendous opportunities for new businesses in these regions rolling out this technology.
Thank you, Dr. Shearer. Can you go into more detail about the liability challenges of using robots in agriculture? Todd, Janzen?
Sure. I'm happy to speak a little bit more about this. Well, in the United States, our whole liability framework is based upon the idea that whoever causes the harm is the person that should be liable for the injury or the damages. And that works pretty well when you have normal machines that a person is in control of. When you remove the human being from that type of situation, and now you've just got a robot doing a task, then it gets murkier about who would be responsible if that robot does something that causes damage. For example, an autonomous sprayer that oversprays or causes pesticide drift somewhere where it shouldn't have been. Who's ultimately going to be responsible for that? And so, if you had somebody driving that sprayer, it'd be really obvious who's liable. When you don't, then it becomes a question of, is the owner liable? Is the software developer liable for, was it a programming mistake that caused the damages, or the manufacturer of the robotic device? And, the way we answer this question is by assigning the liability in license agreements. So when somebody buys a robot, they in that license agreement, they'll have to say that they are going to be responsible if that robot does something wrong. And so I think it will be a sign of our industry maturing in robotics when we start to see manufacturers take responsibility for things that go wrong from their robots, instead of still assigning that to humans that own them in order to pass the buck, as it were. And so, in many instances, we still require human supervision of robots, even though in reality, that isn't what happens.
Thanks, Todd. Thanks for that excellent explanation. Yeah, so as researchers and engineers, we really don't think about, all those aspects, thanks for that answer. So the next question is, you mentioned there's very little data showing an economic benefits for using the US, I'm assuming here, yeah. Does that imply there's data, but the majority of which does not suggest an economic benefit, or that there's insufficient economic cost benefit analysis as of yet? Yeah, I would like Mike Sama and Dennis Buckmaster to answer these questions.
Sure. I think it's a little bit of both. There is some data out there, but it's small scale, very localized. And most of it's just a function of where the technology is. It's pretty immature at this point. So most of us are really focused on just proving that the technology works and aren't really looking at what the economic benefit is at this point in time.
I would agree with Mike, certainly on that one, especially early in the development of any technology. It's hard to prove the value because we don't actually know what the real cost is going to be when it's implemented at scale. And so that takes a little bit of time to work out. But we probably should certainly take that as good advice to collaborate with economists more often. Thanks for the suggestion.
Thank you. So the next question is, how are students at the universities represented on this panel, helping prepare future agricultural workers to effectively use or manage these evolving technologies? Yes, Scott, Shearer, and Dennis Buckmaster.
Yeah, I'll start off with this, and I know Dennis is gonna amplify what I have to say here, but I think about the educational demands to help people stay current in agriculture as these new technologies come on board. And I think about those in a couple different lights. A lot of effort has gone into things such as artificial intelligence and data mining, data science, if you will, in terms of agriculture. We see a lot of companies amassing a lot of data. But I want to emphasize it's not simply a data scientist analyzing a data set. There has to be a subject matter expert. And I think when we fail to include the subject matter expert, there could be disastrous consequences, so to speak. As we move forward, we have to get our graduates of colleges of agriculture comfortable with the terminology and a basic or fundamental understanding of how data mining or data science or artificial intelligence manifests itself. Now, we're not going to make data scientists out of the subject matter experts, but by the same token, they're going to have to work with data scientists as we move towards the future. We're going to have to do this on many fronts for our current students, for our graduates who are out in industry and in terms of retraining. But we also have to begin thinking about some of those agricultural professionals that are place bound and probably are not going to come to universities. COVID-19 has changed how we look at distance education in some respects. So it's going to be an interesting time.
Concur and echo. I think it is also going to be more important for these two-year degrees. So, you know, most of us here on the panel, we're at land-grant institutions and we probably don't offer those two-year degrees. But the graduates from those programs, the community colleges, et cetera, that have some discipline knowledge, but sort of closer to the ground, so to speak, their importance is, you know, it's going to be important that they know how to work with engineers, data scientists as well, because they're sort of the boots on the ground.
Thank you. Thank you both. The next question is, how widely are robots adopted among specialty crop growers? For example, the apple harvesters. Are there USDA surveys for automation? I think this is a really good question. I think we might have to get back to you with some specific literature on that. But our co-author Manoj Karki, he cited some literature on apple harvesters, and there are at least a couple of companies that are offering apple harvesters that could be available soon, but I don't know all the details about that. So we'll be happy to get back to you on this question, where we are in terms of apple harvesting robots and what are the adoption rates. So. The next question is, are there any concerns regarding the safety of these upcoming technologies? Todd?
I'm sure. I think, you know, it's a pretty diverse question, right? Because there are various safety implications depending on what type of technology you're talking about. You know, when UAVs really came on the scene, we heard a lot of safety concerns with respect to them in US airspace, but it seems like that's settled down and things have calmed down now. But for me, I think when you're thinking about safety, the question to answer is the robotic technology safer than the human alternative? And that's what you should really shoot for if you're developing these. And, you know, not making people or animals your guinea pigs, but making sure the technology is safe by the time it reaches the market.
Thank you, Todd. So the next question is USDA funding work on use of robots? Are organic farmers more or less interested? Any studies on economic impact for organic growers? Scott?
Okay, I'm going to use an example that's right here in the state of Ohio. We have a number of vegetable growers up in the peat and muck soils up around Willard, Ohio. The interesting thing is these growers have traditionally grown 15 to 16 crops in this area of Ohio. And the interesting thing is they're losing registration of herbicides. And so today, with some of the tightened rules and restrictions in terms of migrant laborers, these farmers are being forced into a very untenable situation. And so we've been trying to get them to adopt some technology in the hopes that they can preserve their operations in that part of Ohio. Yes, it's an herbicide-driven issue in some respects, but one of the things I point to is, when looking towards the future, is technologies such as artificial intelligence. We're able to discriminate between the plant and the weed in this case. And I want to even fast forward to the point that when you're able to specifically spray the weed, virtually anything becomes an herbicide. And when I make that statement, you know, hot oil might be an herbicide. And so I want people to think about how some of this technology may replace some of the existing technologies that are in use. We genetically modify a lot of crops so that they're resistant to certain herbicides. But again, if we can pinpoint and spray the weeds only, that changes how we view things going forward. So I think there's tremendous opportunities for organic producers with technology, and we can start out with mechanical cultivation, but then I think it extends well beyond that.
Mm-hmm. Thank you, Scott. So I think you kind of answered a part of the next question too. So where are we in terms of precision application and the use of robots and machine vision, especially for areas other than herbicide use? For example, do we have technologies to spray only a certain parts of the plant, trees, vines, in academia or research leading in this area? So yeah, Scott and Dennis.
Well, briefly, we have a group of ARS scientists in Worcester, Ohio. They're embedded within our academic unit, but they've been working on a technology where they're using rotating LiDAR to map out the tree canopies, and then smart nozzle technology, if you will, that only sprays when their foliage density is an appropriate level. And so I know that Dennis is going to talk about vision technologies, but the important thing is there are multiple technologies that might be used in these type of smart spray systems.
Yeah, this is a good area for the sort of the sensor fusion approach. LiDAR, like Scott mentioned, is a really good one. But you could use sonar, you can use vision technologies to essentially generate a 3D model of what you're looking at, just like a human could. Of course, that all requires training, which is a good amount of data to drive those artificial intelligence models. Just looking at the question, I'm remembering some work out of Dalhousie University on the eastern edge of Canada there. This was several years ago, where they were using some, at that time, sort of elementary, what we would consider now anyway, vision technologies to just identify, is there anything here to spray or not? And of course, a human could do that, but to do it in an automated way, even before we get fully to robotics, to automate part of the operation is a step toward full autonomy. I think we do need to remember that all of those little things we do to make machinery work better, to use less product, to self-adjust, those are steps toward full autonomy.
Mm-hmm. Thank you to you both. So the next question is, I'm trying to understand this question fully. How did you design the edge nodes in terms of position, coverage, bandwidth, power, and etc.? I think you're referring to maybe the farm connectivity and how we can install edge nodes, and then how can we implement some wireless infrastructure so that we have more coverage and bandwidth. I'll take a shot at this, but then I'll let other panelists to answer this. I think in terms of the farm connectivity, no single solution will solve all the problems. So we're talking about there's a LoRaWAN technology, but then there's a TV white space. And then there's millimeter wave technology. So there are a lot of different wireless connectivity technologies that could be used to transmit information, and not just text data, but also images and video feeds. So I would say multiple wireless technologies are needed in a way. And Dennis, would you like to answer some of this question too?
We'll just chime in that there is no one solution. It depends a lot on the frequency of the data, essentially the data rate that needs to be sent. For some things, you need to be sending sort of live video streams, or at least static images very frequently. That will require certainly Wi-Fi, cellular, TV white space with bandwidth. For things that are infrequent, like where are you, sort of the status of things. Actually, you could send a fair bit of control area network data as long as you were just choosing the right parameters, the right measurements. You could send that via LoRaWAN also, with at least a decent frequency. So much of this is a function of exactly what is it that you need in order to make that next decision, or automate the processes. And so it depends on what you're trying to automate. Are you just trying to automate when does the tender truck show up and how much should be in it? Well, you could communicate all you need for that with a LoRaWAN, very inexpensive and very long reach.
Yeah, I think thanks, Dennis. And in the paper, we have more use cases that are discussed. So yeah, please refer to the paper on this one. Then the next question is, I got a question about power supply to UGVs, USS. While these devices require frequent charging, how could it be possible without or with least human involvement? Michael?
Yeah, sure. And actually, this question came up a couple of times in different iterations in terms of like flight time and stuff. So maybe I'll handle the other questions as well as part of it. But there's several startup companies now that have charging pads that you can land on that will charge your system autonomously. That's relatively slow. There's also robotic systems that will swap the battery out. Not very common. I mean, I think that's geared towards autonomous systems where you want to deploy a platform, multiple times throughout a day or over a longer period of time. In terms of overall flight time, though, it's actually improved a lot recently. If you're using fixed wing planes, we have systems that fly 2 to 3 hours, which is far more than what you could ever cover using visual line of sight rules. So within the existing FAA framework, the flight times are pretty good. And multi-rotor systems are approaching an hour now as well, too. So you can cover many, many acres. And, again, you can cover everything that you could possibly see within one flight.
Yeah, thanks, Mike. And I'll try to answer the ground robot aspects, and Scott, you can join in. So one of the, like battery charging is going to be not practical, at least for field robots. Just because of how much time it takes and how much power density you need to do actual field operations. So one of the things that we're looking at, we're using internal combustion engines on the first robot I showed you earlier, the 60 horsepower machine. It's a CAN-enabled internal combustion engine. So you can do quite a bit of interface quite a bit of electronics with that type of machine. So that's one way. Until the battery technology is matured enough that we could use it in the field at an affordable cost, I think going with a internal combustion engine, it might not be a bad idea. So Scott, do you have any?
Yes, Santosh, the only thing that I would add, I think it's going to be much more realistic to see electric vehicles in the field for low draft applications, and the example would be spray application. When you get into high draft tillage application, I think you're 100% correct. It's energy density, and it's being able to perform that operation continuously without interruption.
Thank you, Scott. The next question is, can you please provide some idea of how much farmers may expect to pay for farming as a service? If you could give an idea, for example, of how much an apple grower might pay for a robotic picker. Yeah, Scott.
Yeah, and I'm going to answer that in a couple different ways, but I think the bottom line is for any of this automation to really take hold, it's going to have to be done so at a cost that's less than what the producer or the farmer is currently paying. And so again, as we see labor shortages, obviously the question is going to be a trade-off. Can I afford to hire a farming as a service business to come in and harvest my apple crop? I also want to get people thinking a little bit about pay for performance. We hear that coming from some of the genetics companies, but when I look at Sabanto, and you talked about Sabanto a little bit earlier in your presentation, Santosh, it's a company that is basically seeding in terms of farming as a service. But again, if that company is able to hit a certain window for planting a corn or soybean crop in the Midwest, there should be greater value there than if they were to plant outside of that window. And so again, as I look, if we're harvesting apples for juice, it may be one scenario in terms of the operation. If we're harvesting them for the fresh market and obviously going into high-end grocery stores or something, obviously there could be a different price point for that. But again, in almost all cases, it's going to have to be below what people are currently paying. Unless, of course, there's that element of value add for hitting a certain window or certain time, if you would.
Yeah, thanks, Scott. The next question is, are there examples of ground and aerial systems interfacing together, perhaps for applications in combined imaging, pest verification, and management? Dennis?
Actually, there is another question posed a little later that's very related, so I'll follow Mike's lead and combine them.
Sure.
I think in part, this is sort of the dream of tomorrow. I don't know of solutions that are out there today, but certainly it doesn't take much stretch of anyone's imagination to think that UAS would fly over, do the imaging, an algorithm would do its work. It might then conclude that, well, there's a really small spot and it needs just a very small amount of something. We can send a different UAS out to actually treat that small spot. Or the algorithm might say, well, there are a couple or 3 acres here that need a particular treatment of some sort. And in that case, we deploy the ground robot in that case. So to do all of that does require a good degree of interoperability, a good degree of rapid computation and connectivity to make it happen. So therein lies sort of the need for the infrastructure behind the autonomous vehicles themselves. We need the sort of the systems that do the sensing, the algorithm, and the deploying and the control to work together well.
Yeah, thanks, Dennis. Yeah, how long until you think autonomous robots will be commonplace in row crop production? Yeah, so Dennis, and I'll follow up.
Oh, good. I'd be glad to hear everyone's response to this one, actually. This is just one opinion, my opinion. We're certainly going to see it growing slowly over the coming years, but I don't think I would use the word common until maybe a decade from now. That's just one opinion.
Yeah, I think my view is, I think we will go through different autonomy stages. I think we might not get to fully autonomous, at least for a decade or so too, so it could be supervised autonomy where a person is still monitoring the machine. And again, some of the first field operations could be fully autonomous or supervised autonomous spraying. And operations like harvesting and tillage, those could be some of the later ones that might come into practice. So Scott, Mike, any ideas?
I'll throw in just a couple other thoughts here. Everybody's thinking about the labor market in terms of what might drive this shift towards autonomy. And in some industries or some areas of agriculture, that's certainly going to be true. But I also think about other things. Right now, one of the ways farmers in the Midwest compensate for labor shortages in some respects is they just buy bigger equipment, okay? And my concern there is what we're doing in terms of the soil profile and the damage in terms of compaction that we're driving much deeper into the soil profile. And so one of the things that I'm suggesting might reverse that trend is go to small autonomous equipment. I think you're right, Santosh. It's going to be supervised autonomy before we get to fully autonomous equipment. But again, there are some other market factors, some externalities that I think we have to be thinking about in terms of this shift and what's going to drive it.
Mm-hmm. So thanks, Scott. The next question is, are there ideal robotic system cost to net and gross operation profits and costs that the community is researching? So Tami, do you want to talk about this? Tami, can you hear us?
I'll unmute. So there's a lot of potential for robotic systems and sensor systems in livestock production. We have to be really careful how we go forward in applying that. I saw a couple questions on UAVs, and one for livestock monitoring and one for livestock herding. So as I think about that, there are a couple companies out there looking at using UAVs for livestock monitoring. But if you want to use it for livestock monitoring, we can never use them for livestock herding, because you want to get those animals really accustomed to the UAV and not change their behavior when the UAV comes over. If you want to use them for herding, you don't want them accustomed to UAVs, because you want them to walk away or run away from the UAVs. So these are really very, very different approaches to how we want to use UAVs or robotics. So I think we need to carefully respond or carefully plan out exactly how we want to apply those, and pick and choose what will benefit the farmer the most.
Yeah, I think that is a very, very interesting comment, Tami. We talk about crop production where crops don't react to machines, right? Or at least they don't react to robots. So here now we have animal systems that actually react to robots. So we need to think about their behaviors too. So that's a very interesting comment. Thank you.
Santosh, I'm going to jump in. We've got a lot of questions. We're obviously not going to get to all of them in this period, but I do want to take this opportunity to thank you and thank all of our panelists for being on today. And thank you. We will collect these questions and the ones that we did not get to during our presentation and get those answered and posted to our website. So please continue to look for that, and you'll see posted in the next week or so. Maybe questions, all of these answers. I'd like to again remind you, if you've not seen the paper so far, it is available on our website, www.castscience.org. And if you go to the publications tab, you'll find this and all of our other publications listed. Again, all of these publications are free, and we hope that you look to CAST as your trusted source for science information. Again, thank you for being here. Again, thanks to Santosh and all of our panelists today who did a great job of sharing information and sharing, answering the questions that were posed today. Thank you for joining today's webinar, and we hope you'll be back on future webinars in 2021 as we begin our next series of paper rollouts. Thank you, and have a great day.
Thank you, everyone.
Thank you.